Hello everyone, my name is Linhan Meng. I come from Department of Computer Science and Technology, Nanjing University. It's my honor to introduce our work for you. The title of our work is Training Data Debugging for the Fairness of Machine Learning Software. Machine learning software has penetrated many aspects of our daily lives, whose results are employed in high-stake applications to make decisions or predictions. Along with the widespread usage of machine learning software, the concern about its fairness has also been raised towards developers, users, and regulators of machine learning software. The unfairness of machine learning software usually indicates the discriminatory treatment of different groups divided by sensitive features, for example, sex. Researchers show that biased training data may lead to the trained machine learning software with statistical discrimination from two angles. The first is the size of feature size, and the second is biased labels and imbalanced distributions. This paper deviates from previous studies as it adopts a different angle. The root cause of the unfairness could be biased features in training data. Here, we define biased features as features that are highly related to the sensitive feature in training data. To obtain unbiased features, we try to debug feature values in training data, which concludes two main steps. First, we identify which features and which parts of them are biased, and then we exclude the biased parts of such features to recover as much useful and unbiased information as possible. To achieve this goal, we propose a novel method, linear regression-based training data debugging, which employs the linear regression model to identify the biased features. Before we introduce our method, we propose a detailed motivation example to show why and how features are biased. We take a snippet from the campus dataset, which is used to evaluate the possibility of a criminal defendant reoffending. The snippet contains 6 samples, with the sensitive feature race and the non-sensitive feature age. We can see that bias between race group is observed in training data. All 3 white people are labeled as no reoffend. In contrast, only 1 out of 3 non-white is labeled as no reoffend. There is a high association between race and age. The age values of the privileged group are relatively much larger than that of the unprivileged group. Larger age values imply white people. The race bias may be introduced by the age values when training machine learning software. To obtain unbiased features, we have to debug feature values in training data. The main idea of our training data debugging is to apply the linear regression equation to analyze the association between non-sensitive features and sensitive features. We employ wild test with t-distribution to check whether the null hypothesis holds. In this snippet, after translating categorical variables, white or non-white, into numerical variables 1 or 0, we have the following linear regression equations. We found that p-value is less than 0.05 and obtained the estimates A hat is equal to 30 and B hat is equal to 6. Xn hat is the explained variance in the original non-sensitive features Xn by the sensitive feature Xs. To exclude the biased parts from the training samples, we consider Xn height as the biased parts of Xn, remove Xn height from Xn, and denote the remaining unbiased parts as Sun. In this snippet, We obtain the unbiased age value HU by subtracting the predict values. HU is equal to age subtract age height. We can see the distributions of age values under privileged and unprivileged groups become independent of race after removing the biased parts. Is to say the revised age values in two groups are the same. We employ 9 datasets to evaluate the performance of our method, all of which have been widely used in previous software fairness studies. Since there are two sensitive features, sex and race, in two datasets, adult and campus, we convert the 9 datasets into 11 scenarios by considering one sensitive feature in one scenario. For example, the adult dataset appears twice as adult sex and adult race. As described before, our method LTDD is a pre-processing method. Is to say that debugging training data before the construction of machine learning software to reduce the bias. We introduce full fairness methods as the baselines. Two state-of-the-art methods, FairWay at FSE 2020 and FairSmooth at FSE 2021, and two widely used pre-processing methods, reweighing and disparate impact removal for comparison. The increasing of software fairness may damage the performance, which is called the accuracy-fairness trade-off. Our experiment focuses on both fairness and performance metrics to check the relationship between fairness and performance changed after applying fairness methods to the machine learning software. We use DI and SPD as the main indicators for fairness. DI indicates the ratio of the probabilities of favorable results obtained by the unprivileged and privileged classes, while SPD represents the difference between the unprivileged and privileged classes to obtain favorable results. For the performance indicators, we choose three that are widely used in the researches: accuracy, recall, and false alarm. In research question 1, we want to ensure how well our algorithm improves the fairness of machine learning software. We first need to check whether our method can eliminate the discrimination that exists in training data. Meanwhile, we hope that our method can damage the performance of machine learning software as little as possible. We choose logistic regression as the main classifier and report the change of our method applying to the original machine learning software on fail indicators. For DI and SPD, the more negative the difference observed, the more our method improves the fairness of the standard classifier. As can be seen in the figure, our method can greatly improve the fairness of the original machine learning software and slightly damage its performance. In research question 2, we want to ensure how well LTDD performs compared with the state-of-the-art fairness algorithms. We hope that our method can achieve that. Compared with baselines, first, it can better improve the fairness of machine learning software, and second, the negative impact of our algorithm on performance would be less or comparable. The comparison results under fairness metrics are shown in this table. The gray background in the table indicates that our method has won the result of the baseline, which is to say that the Wilkinson p-value is less than 0.05 and the cliff delta is greater than 0.147. The black background indicates that our method loses to the baseline, which is to say that the Wilkinson p-value is less than 0.05 and the cliff delta is less than minus 0.147. The white background indicates a tie. It can be seen that, first, Our method is superior to other baselines in most cases in terms of average values. Second, our method has won the baselines in 37 out of 55 cases under DI and 38 out of 55 cases under SPD. Third, compared with the best baseline, Ferris mode, LTDD has comparable performance under DI, while it performs better under SPD. We list the comparison results and the performance indicators in the next table. To compare the effects of different models on the performance loss, we compare our method and baselines with the results of the original classifiers without applying fairness algorithms. Generally, our method has losses to the performance of the original classifiers. In terms of accuracy, recall, and false alarm, our method significantly damages the performance of the original models in 10 out of 33 cases, which is less than 3 out of 4 baselines. Besides, our method has only 2 cases with significant damage under false alarm, which is the best among all fairness methods. It can be said that our method performs better than baselines in the improvement of fairness indicators with the performance damage less than or comparable to baselines. Then, we verify how our method compares with the state-of-the-art fairness algorithms under different classifiers. We also conduct our experiments under 2 other classifiers, naive Bayes and support vector machine. We show the comparison of fairness metrics for the 3 classifiers in the above table. We count the number of win, tie, and loss cases compared with the baselines and summarize the results of the 3 classifiers together. When the number of wins is greater than or equal to the number of ties plus losses, we mark this column with a gray background, which means that our method is significantly better than the baseline. In 7 of 8 scenarios, our method is significantly better than baselines. We list the comparison results of performance indicators in the below table. We compare the 4 methods with the results of the original classifier and count the number of win, tie, and loss. Our method has the least number of losses in terms of accuracy and false alarm compared with the original classifier. With 3 different classifiers, our method still defeats baselines in most cases under fairness indicators and has the least loss under accuracy and false alarm. In research question 3, we introduce a new indicator, the rate of favorable decisions. To measure the actionability of fairness methods, our measurement is based on the following points. First, in realistic scenarios, the rate of favorable decisions is limited due to the finite social resources. For example, for the loan application, the rate of approval is restricted. Second, before applying fairness methods, original machine learning software has made favorable and unfavorable decisions, among which the original favorable rate could be considered as a benchmark. Third, after applying fairness methods, machine learning software might change the favorable rate. If the favorable rate essentially increases, it would also raise the need for social resources, even beyond the boundaries of available social resources, reducing actionability. In this research question, we will compare our method with Ferris mode under the new indicator. In this figure, we employ 2 endpoints to indicate the favorable rates of the privileged and non-privileged classes and connect them to draw a line. The short horizontal stroke indicates the whole favorable rate. The figure's red, blue, and green points represent the original value, the result of Ferris mode, and that of LTDD, respectively. In 10 out of 11 cases, the way that LTDD improves fairness is to increase the favorable rate of non-privileged classes and to reduce the favorable rate of privileged classes, so that the whole variable rate is very close to the original value, while first mode tries to increase the variable rate of privileged and non-privileged classes, resulting in a significant increase of the whole variable rate. This means that the implementation of first mode needs much more social resources. In next few minutes, we discuss some interesting tips. First, we observe the distribution of biased features. We judge whether features are biased according to the p-value generated by valid test. The figure shows the average proportion of biased features in 11 scenarios, where the blue bars indicates the proportion. In 8 out of the 11 scenes, the percent of biased features are over 60%. Besides, we have also observed that the proportions of biased features in the three datasets, bank, student, and German, are the lowest three. According to the result of research question 1, the fairness optimization effect of these three datasets is also the worst among all datasets. We argue that the proportion of biased features may be related to the fairness improvement effect of LTDD. Then, we want to use an example to show how our method eliminates biased parts from biased features, narrowing the difference in these biased features between privileged and unprivileged classes. The figure is the distribution of the age feature for privileged and unprivileged classes on the campus dataset. Here, the privileged group is white people, and the unprivileged group is non-white people. The orange dotted line represents the median value, the purple triangle represents the average value, and the green diamond indicates the outliers. After removing the association between the age feature and the race feature, we can see that both sides of values have been shifted, which makes the distribution between the two groups closer. Our method narrows the distribution difference between the privileged group and the unprivileged group. To verify the performance of our method and the other fairness indicators, we compare our method with the state-of-the-art method, first mode method, and the other two indicators, AOD and EOD, with three classifiers. AOD is the average of difference in false positive rate and true positive rate for unprivileged and privileged groups. EOD is the true positive rate difference between unprivileged and privileged groups. As can be seen from the table, our method is slightly better than first mode in most scenarios. The average value of the two indicators of our method in the three classifier is lower than first mode. Here, lower means more fairness. To conclude our work, we adopt a new perspective for fairness testing. The root cause of the unfairness could be biased features in training data. To improve fairness, we propose a novel method, LTDD, which employs the linear regression model to identify the biased features and exclude the biased parts of such features. In the future, we hope to conduct research on more extensive datasets to explore different characteristics of the datasets. That's all. Thank you for your listening.